This conference will now be recorded.
Okay. So good morning, Padmini, and welcome back to a fresh new session on market risk modeling. We'll start off with a quick recapitulation of the concepts that we had discussed in yesterday's session, and from there we will kind of take it up. So one of the important concepts that we had been talking about in yesterday's session was the concept of a structural break. So one of the things that we intuitively we had seen was that in the presence of a structural break, the augmented Dickey Fuller test can end up providing a misleading conclusion about the stationarity of the time series. Right. So therefore, one of the important objectives that we would have over here is to delve a bit deeper into these characteristics and try to identify how exactly is it that these structural breaks work. So how is it that we can identify structural breaks? It's one of the very simple ways of identifying the particular structural break was a rolling sample test because it, because we saw that it could overcome the it could overcome the biasness that is there in these estimators. So biasness which is there in the ADF test. Now, so over here, what we are going to do is we are going to delve more deeper into the characteristics of structural breaks, right? So, how does a structural break happen? How does the prediction or how does the identification of stationarity go about in structural breaks, and why is it that uh, ADF test fails to apply or to identify structural breaks in the data? So, so this entire framework is something that we would need to kind of identify as we move forward, right? So as we would kind of look into this, as we would kind of move forward. So, and then from there we need to understand that how is it that a structural break is identified using a Chow test, right? And what are the next steps? And given that you identify a structural break, how do you choose your data? The next point would be to, given that your series is non-stationary, you identify a non-stationary series. How is it that you would kind of go about doing this or performing this analysis? So how would you go about detrending a series and so on? So that is what we are trying to do. Okay. So the first question that comes out over here is that structural breaks. Now, when I talk about structural breaks, how does that structural break look like for us? So first, let's construct a structural break uh, for this discussion. Right? So we had drawn a very rough sketch of structural breaks, but let's look into it in a more detailed manner. Because from here we will be able to identify the limitations of ADF in identifying these breaks. So this is the origin axis, the axis of origin. This is time, and this is the variable yt. So whatever variable it is. Now, one of the things that we saw was that a structural break would generally lead to a permanent change in the trend. the trend. Okay. So how does the series look like? So the series happens something like this. There is a certain break over here. Right. Now that can be upward as well as a kind of a downward. But then again the series kind of remains over here. Now if we have a look into this, so this is the point of the structural break, or this is what I'll call the critical point. Right. So this is the critical point T. Now over here, the question that comes out is that how do I assess whether this is a test, like whether this is a, so whether this is a non-stationary or a stationary series. Now, if you take the whole breadth of the data, so if you take this entire horizon of the data, right? So what will you see? What you will see is that, so if I take this whole breadth of the data, one of the observations that I'll get to see over here is that yes, this series is something, so where so which is non-stationary in nature. So the question that comes out over here is that what would be the best fit line which can approximate this series or approximate this particular time series. So let us go back. So let's use a very simple Excel example first and try to understand the kind of challenges that this can actually pose. Okay. So so this is where we are trying to simulate the structural break simulation. So let this be time. So one, I will kind of try to automate this. So let's say I'll take 100 data. Right. Now over here I am trying to simulate my series XT. Now XT is the time series variable. The time series variable. So let me so I'll just random it between. So let's say 100 to 300. Right? So the first 49 records that I will have over here is between 100 to 200. Now, now from here, I am just directly changing the series from between 1000 to 2000. I'll put 1000 over here first. Then I'll take the rand between. Now from here onwards till the last. But the first, so this is the point of jump, and I'll fix it at 1000, and then you have the different one. Let me put it at 1000. So, okay. So now more or less the series is giving me what I need. Now let us try to. So I have just fixed this set of series value over here. Okay. Okay. Now what I'll do is I'll plot a graph. So I'll plot a trend line. Yes. So now this is what I was talking about. Now observe that in this particular series, right, the series that we have over here, So the series that I have over here is something, you know, like this. Okay. So over here in this particular sub part, there is a typical kind of a mean between 100 and 200. And over here, there is a different kind of a mean, right? So now the question is, so the only point where the jump has or where the changes has happened is at this particular point. So let's try to fit a trend line to this and let's see how it works out. So first what I'll do is I'll also label this graph, primary horizontal and the vertical axis. So this is the months and this is XD. That is the time series. Okay. Now the next question is, so this is the structural brick block. Right. Now let us see. Now let us fit a trend line to this. And what I'll do is I'll fit a linear trend. So this linear trend line that we have fitted over here. Now let's display the equation on the chart. Right. Now the question is that how did I get this linear trend line? So this linear trend line has been obtained using the same linear regression formula that we saw, right? So this is obtained from the OLS method. Now look up, now this linear trend line has a very typical property. The property that this linear trend line has is that it can or it is more closely approximating these higher end values than these lower end values, as you can clearly see. So it is more closer to these higher end values, right? So obviously the trend or the linear trend of the time series gets impacted or influenced by the high end values, right? And that is a very typical property of a linear regression or of a linear of a linear regression exercise. So you tend to, if your series has high ended values, they tend to get, then it tends to get uh, you know then it kind of tends to get uh, what should I say, so it tends to get biased towards the higher end values. Now the question is that if I were to use an ADF test on this series, right, so will this ADF test be biased towards non-stationarity or towards stationarity? Right. Now let's say now the question that comes, so the next thing that I need to address over here is that I need to understand is the nature of the ADF tests. Right. Now this is obvious. So the series that we initially assume is a one state series. So it's a one lag series that I'll assume. So let me assume an AR1 process or an autoregressive one process. And let's fit a time series to it. And the equation that I am kind of using over here is I will be using a very simple equation and a simple AR1 process, and the coefficient that I am talking about is this one. So you can see that y is equal to 2.28x minus 161.59, right? So let's say that 20. So basically, what I'll do over here is I will just use an arbitrary equation, arbitrary coefficient for the AR1 process, and from there I will try to explain a typical feature of the AR1 process. Now note that the regression coefficient of the AR1 process is estimated through this regression coefficient. I mean, is estimated through the OLS estimation process. Right. Well, so we'll see how it gets done. But over here, I will be using an auto-regressive model over here. Auto-regressive model. But over here, I'll mention it to be hypothetical so that we don't come across we don't get confused that how has it been actually calculated. So over here, let's say, so this point will be blank. So the equation that I will have over here is, let me see, let's say it's 0.91 star. Right. Now this is what the series is. Now have a look into, so now we will see a typical nature of this AR1. So the way the AR processes are structured, and that will explain one of the important reasons of, or one of the important limitations of the AR1 process. So let's see this. So okay, to see this, let me just plot this graph over here. Oh, now observe that. Okay, so now observe this image. Now over here, what is happening is, so you will see that. So if you have a look into this part, so corresponding to 268, it is 121.94. Then it's 243, 284, 151, 221, 258, 113, 201. So you can see that it is very, like, if I expand this graph a little bit more. So one thing that you can see over here is that this graph, right, is like far, I mean, the observed and the predicted values are literally far away, right? And when the values are lower. So corresponding to 278, it is predicting 91, 183, corresponding to 100. So the predictions are much far away. So they are less accurate for lower values, right? But the moment the value switches over, right? So the moment the value switches over to 1000 and all, you can see that the prediction starts becoming closer and closer, right? So over here, by the time when you come down to these points, you can see that finally 480 corresponds 1550, like this. So so in this case, if I try to apply the ADF test on this, so one of the limitations that this AR1 process has is that it works on a typical assumption. And what is that assumption? And that assumption is that lower values lead to lower values, and higher values will lead to higher, like subsequently higher values. So basically, when there is a sudden structural break at one point, right, the AR1 process is unable to distinguish between them. Now, had it been able to distinguish between a structural break, right, then it would have been using this long run trend and then making its predictions. But over here, you can see that it immediately adjusts it to it and then you keep on predicting. So now if you actually use the long-term series of this entire data series for your predictions, right, and you try to assess the stationarity, your estimate, your row that you will calculate will get more biased to one, because OLS, because over here when you are okay, so this will get complicated. Let me just break this down a little bit. So the first thing that we can see is that when I'm plotting a linear model, or a linear autoregressive model over here, the autoregressive model is 0.91 into xt minus 1. So xt is equal to 0.9 into 91 into xt minus 1. So in that case, you can see that the moment there is a structural break and it rises, the values get more closer to the actual value, right? And in this case, the values are much lower in this part of the series. So one of the assumption on which this particular model works is that this model assumes that lower values of the time series will lead to lower values and higher values of time series will lead to higher values. So the moment the value changes regime, right, this estimate, this linear model is unable to distinguish between the two and it moves on to a higher value. So now, if you look into the differences of the impact of the values in between two lags, what you will see is that so if I consider the difference between this point and this point, there will be a sudden increase, right? And that impact of the increase will remain on any of these two. So that one increase, that one difference in the lag, one increased difference in the lag will impact the ADF test statistic, and that impact will cause that gamma and that beta to rise suddenly, and hence the entire ADF test will start tending towards will get biased towards that rho equals to 1, right? The only reason over here is because if you look into this function, you'll see that this is 1 minus summation AI. So it's a linear function of the AIs. Now, if there is a sudden switch in one part, this part will get affected. This linear summation will get affected. And therefore, this gamma will get biased towards the null hypothesis being accepted, right? So, and in such a case, you will always tend to reject the you will always tend to accept the null hypothesis, and your test will get biased towards the the test will get kind of biased towards the what should I say? So it will get biased towards non-stationarity. Right. Now this is also identifiable from this data as well. So let me just so this is your time variable, and this is your the time series variable. Observed versus AR1 hypothetical prediction. Okay. Now let us have a quick look into the nature of the time series. Now let's say I take the first 10 observations. So what is the mean over here? The mean is 197. Now I take the mean from 10 to 11. So you see it's 195. Now I take from 3 to 12. So it's 187. So one thing you can see is that the mean that is, so whatever the mean figure you are getting, it's like 197, 195, 187. So the distribution is more or less very symmetric, right? So if you take from, let's say, 4 to 13, so it's 193. Then you take from 5 to 14, it's 192. So that entire thing lies between 197, 187 to 197. So there is a well charted out interval of the values, right? So one thing you can see is that if you take separate subsamples, right, and you look into the mean, you will keep on getting, or let's say you will always get values which are like more or less coming similar, right? So they are more or less lying in that similar bracket. Now, what you do is you come back over here. So we come back to the 50th observation. Let's say 1, 2, 3, 4. So the average over here is 177, right? Now I move from 38 to 47. The average is 192. Then 39 to 48, the average is 189. From 40 to 49, it is 188. Now I move from 41 to 50, you see suddenly this goes up to 272. Now if you move from this 42 to 51, your average is 392. So now this is where your average actually starts shifting, right? So when you are doing the rolling sample, whenever the structural break keeps on coming, you will see that your mean is getting shifted. It is getting shifted from that long run average that you are looking into, right? So it is this existence of this one shift, right, which will create causing this problem. So now you move from 43 to 52, it's 518. 44 to 53, 669. So this is where your series has started becoming unstable, right? And you will actually see, so if you do a long run plot, you will actually see that there are triggers around this point, and it is because the nature of the data had changed from the 50th point onwards. So now when you go from 50 to 59, you will see 1407. You go at 51 to 62. Sorry, 60 is 1464. So now again it has started stabilizing. So from so if I divide it into 1 to 49 and 50 to 100, you will see that it has currently, like, so you can divide it into two clear subsets, but it is because of the existence of this particular point that the whole mean series or the mean distribution is getting changed. And that is why when you will calculate, so when you fit a linear OLS regression algorithm and try to calculate the AR1 process, that coefficient, right, will get shifted towards, will start getting shifted more towards 1. Because what is the formula of that rho? That rho is nothing but the covariance between two terms divided by the variance of that xt, right? So so that particular, so both covariance and variance are linear functions about the mean. So if the mean gets shifted, right, then your row estimates, or your, I mean, your AI estimates will also get shifted, and hence it will start moving towards 1, because the tendency of mean itself is to get biased towards the higher end values, and hence your AR1 process will also get biased towards that unity, and hence your ADF test will always tend to give it as a non-stationary method. I mean, as a non-stationary time series. So when you do this non-stationary time series, so when you do this, so what you will see is that your data. So even though there are two types of uh, pattern into your data, that one single point is going to bias your output, right? And this is what the key reason of, or this is what the key reason of limitation, or the key limitation of the ADF process is, right? So is this part, so is this concept clear to you, Padmini? Okay. So therefore, the next thing that we need to do is we need to understand that how to solve this problem. So therefore, before doing an ADF test, it is very important that we, since it is a very long run data, right, it is very important that we identify for structural errors. Now, if you see the mean shifting every 12 months and then coming back to normal, you know that there is seasonality. But if you see that it is one particular time point where the shift in the mean is there, but before that and after that the mean has is like near to a long run trend, but two different, but it is converging to two different values, then you know that there is possibly a structural break. So what do I mean by this? So let's say let's use a rolling sample exercise. So rolling sample 1, you'll have rolling sample 2, you'll have rolling sample 3, you'll have rolling sample 4, you'll have rolling sample 5, you'll have rolling 6, you'll have rolling sample 7. So let's see. So I'm choosing the sample. Uh, so I am choosing the sample from this part. 2, 3, 6, 9, 10. See 37. So I have taken 20 rolling samples over here. Right? So this is the rolling sample number. Number. Now this is based on a set of 10 of, so 10 months, or you know, for a rolling sample of size 10. So every time the sample rolls on by 10. Right. So now if you have a look into this, so you will see that till here it was between 170 and 188. So the limit was more or less something. So it was within a given interval. So if you look into the differences, so this is what the max and the mean is. Now the moment this the structural shift started getting incorporated, right? You could see that the values just had moved out. So this was the period when you had to 49 was the last point of before the structural break till uh, so till like 58, right? So from there what we could clearly see is that it is this nature, it is these structural breaks, or the existence of these structural breaks, which was creating this sudden movement. And then again the variable settles down between 1400 something to 1436. So again the band kind of spans out over here. So we'll just check the difference between two consecutive means. Two consecutive rolling sample means. So this is plan. I will just look into the positive, the absolute difference that happens. Now, if I do a conditional formatting, so now look into the distribution over here. So this is what the percentage change is. And once that impact of the structural break is over again, so this is what the impact is. So between this period to this period, right, it is where the structural breaks have been included. Sorry, this to this. This is where the structural breaks have been included. Right. So what is the impact over here? The impact over here is that from here to here there has been a sudden change. If I plot this, right, so you can see that over here there has been a very a disruptive change over here, and then it has kind of started going down. So this is where the impact had actually happened, right? Now the second part is between here to here where the change has, so the entire thing has shifted off from, so from here onwards structural, the impact of the structural break is totally over and you are using data from the structural break onwards and you are working with it. So this is where the next changes happen. In between this is the period which has mix of a structural break and not, right? Now, so this is the period which makes the entire mean series be stationary. So if you look into the overall data, right, so your mean will you will see your mean has shifted from 173 to 14.36 if you look into the whole series, right? So if you look into the overall series, then what will happen is it is because of this impact of this structural break that the entire series mean distribution goes for a toss and your predictions get biased towards rho equals to one. I mean, the unitary root towards the unitary root, and ADF gives you a non-stationary series. So this is basically what the issue with the ADF test is, right? Instead of just, and therefore it cannot address this because it cannot address this break and it applies the data on the entire series. So this is what the actual idea behind this biasness of the ADF test towards the unitary root is. Right? So this is what the analysis is. Now the next question that comes out is that, so basically when you have a data set and you are using it, so this is how you can identify or graphically identify the existence of a structural break. So one is through the simple plot and you can see a clear jump, and then what you can do is you can see you can use a similar mean difference change and identify a structural break. So if the time period over here is something which is different, the series over here is of a different color. In between you have this, and these are the two shift points. So so if you get a similar pattern or if you can create a similar pattern, you can say that yes, there is a structure, right? Any questions up to this point? So Padmini has a question over here that so can we say that there are three parts: blue followed by the red and green, then again yellow, right? So there are three parts, right? Now, so obviously also if you look into the graph that we had drawn, this graph, right? So this is one part. So the mean will be more or less similar over here. So if you look into this part, this is the second part where, so basically when you are doing a rolling sample, you have one part which includes this. So let's say I am doing a rolling sample exercise. Right. So one part will be this part, so which you can see in blue, right? So another part will be this part. So let's say shows the switch in red and the green, and then there will be another part which is overcome by this. So it will be this part. Right. Now coming to your, so there are three parts. Now coming to your next question. The next question is, why is sample rate be increasing again? Now over here you can see that there are certain fluctuations. So if I see sample 20, so it is this part, right? So it has the values over here is higher than the other period. So this is because of the fluctuations, but they are more or less in the 1000 to 2000 range. So you can see that the values will increase. It's not that the mean will decrease, but what you can see is that the mean is in the range of 1400. So there will be certain changes. Now, the next question is, so once you have identified a structural break and you have divided your sample, now the sample that you are going to use will be the most recent sample, because before the structural break had happened, you cannot use that data sample. Now within this sample that you are using now, after the post the structural break, there can be other sources which creates the non-stationarity in the series, right? So it could be the results of seasonality, there could be trend, and then those need to be treated for. So these are the basic checks that you need to do before you are trying to perform a time series analysis. So first, you need to understand whether you can use ADF testing on the data. Now, using an ADF test becomes challenging in the presence of a structural break. So what you need to do is you need to first identify whether there is a structural break. If yes, then the data needs to be appropriately built up. The data samples need to be appropriately chosen. Once that is done, then you come down to applying the ADF test and identifying the sources of non-stationarity, right? And then next we'll talk about the different sources of non-stationarity and how to like remove those sources of non-stationarity and convert them into a stationary series. So if there is non-stationarity, how to deal with them. So how to deal with the trend, how to deal with the seasonality. So these are some of the questions that we would be talking about, right? Okay. So just to summarize your answer, so the series values can increase, right? But with whatever increase and decreases happen, they will happen within a given interval. So like you can see, sample 4, rolling sample 4 also had a very high value and then it fell off. But the series was within 175 to 200 limit, right? Now, so the mean was within that interval, but it suddenly shot up 200 once the structural break got included into the sample. So that is rolling sample 7. And that's the first time the structural break period had been included, which caused it to shoot up and the mean suddenly changed by a certain percentage. But if you look into the percentage changes which had happened, they were well within 10%, 1 to 10%, right? Similarly, in this period also the mean changes are within 1 to 10% range. So that is where that is what is more important, right? To look into the percentage changes in the mean and not on, I mean, so mean can increase or decrease, slightly increase or decrease over time, but whether it is happening within a given range or not, that is more important. So does that answer your question, Padmini? Okay. Okay. So I'll just take a 5 minute break and I'll just be back and we'll then commence the discussion once again. So just give me 5 minutes.
This conference will now be recorded.
Okay, fine. So the next thing that we need to talk about over here is that so we have seen the challenges that structural break poses to augmented so to perform the ADF tests. So now we have also seen a way, a graphical or an intuitive way of identifying structural breaks, possible structural breaks. Now the next question that comes out to us is the following: that how is it that would we, or so how is it that we would uh, identify structural breaks statistically? So, how is it that we would do that? So, for this, what we need to do is we would just, so one of the tests or one of the ways to identify it using rolling sample is something that we have discussed yesterday, and we saw it using Excel. So the next question that is, so the next thing that we would want to, that I would want to explore is the Chow test. The Chow test. Now, what does the Chow test do? The Chow test assesses the difference of mean about the break. So, assesses the mean difference about a break. About a break. So, when I talk about performing the Chow test, so one of the important thing is that we want to understand that given that there has been a dummy, so given that there has been a certain spike, now how do you work? So how do you go forward doing this exercise? Right? So how do you go forward assessing that particular spike? So that is something that we want to understand. So let's see how this particular test is done. Okay, so one of the questions, so over here, in order to uh, define the Chow test, we need to define two dummies. So one of them is called a pulse dummy, and the second is called a level dummy. Called a level dummy. Now the question is that why do we need these two dummies? That is the next question, right? Now we would need these two dummies to frame the statistical hypothesis for the Chow test. So how do you frame this hypothesis? That is the next question. So before we talk about framing the hypothesis, let us try to define the pulse dummy and the level dummy. So that is important for us. So first of all, what is the pulse dummy? So let me denote the pulse dummy with the DP. Now this will take two values, 1 and 0. So the question is that when is it that it is 1? Now the pulse dummy is 1 if t is equal to the capital T plus 1. So if the structural break has already occurred because the break is happening at time point t. So if I want to test that there is a sudden spike, right? Now, if at that point, is it that this chow is there? I mean, is it that, so if the chow has, I mean, if this event has happened, the spike that I am saying, and if, so if this event has happened, right, then the dp will be equal to 1, right? And because of this dp, the mu or the mean should rise as compared to what it was before the structural break had happened. So let's say the average was 100 before the structural break had happened. So after the structural break, the average moves on to 500. So there is a 400 units jump in the overall mean. So this is what the pulse dummy is doing, right? So it is helping me assess whether the thing is, whether the mean is high or not, right? So whether the, so assuming that if t plus 1 has happened, right, then the and the mu has increased slightly. What I want to understand is that whether this increase in the mean is statistically significant such that I can call this a structural shift. So that is what all Chow test will do. So what Chow test will do is it will say that okay, there is a mean for all the values, right? So that we have, and the second is that uh, there is this shift. Now, if the two means are not very different, right, after that new increase and before the new increase, then that is not a structural break. If it was a structural break, then both these two would have happened. Then both these two means would have been very different. So that, so, so the pulse dummy is 1 if for any time period after which the break has already happened. It is 0 otherwise. Right? So it is 0 otherwise. Now the second, so this is what the pulse dummy is. The pulse dummy is. Now the second one is the level dummy. So the level dummy will also take two values, 1 and 0. Now what is this level dummy? So for any time period greater than t, this will be 0. I mean this will be 1, else 0 otherwise. So this is your level dummy. So this is the level. Now what we'll do is we'll try to understand that what is the regression that we are doing in the null hypothesis and what is the regression that we are doing in the alternate hypothesis. So we need to assess. Okay. Okay. So let us try to assess the null hypothesis. Now, as we know, the null hypothesis is always a so it is always a no impact hypothesis. So the null in the null hypothesis, what we are trying to do is we are saying that the YT, the data generation process of the YT is mu1 TP plus ET, where ET is normally distributed with mean 0 and a constant base. The ET follows a normal distribution with a mean 0. Right. So now the question is, what is it that this null hypothesis is trying to tell us? One of the things that you can clearly see is that AT Y1 YT minus 1 plus ET, if I remove this mu1 dp, is nothing but a non-stationary process. So all it says is that if the dp is 0, right, and so then mu1 dp will be 0. So before the structural break, so so let's say dp is 0 means it is before t. And if I accept this null hypothesis, it means that the time series was already non-stationary before the structural break. Right. Now the next thing that comes out over here is, so this is the fact that the time series was itself non-stationary already. Right. But if there is a structural break, then there has to be a change in the mean. So previously it should be stationary. After the break, it should be stationary, but in between, there should be a mean changing impact, right? So that will cause the the level dummy to change. So given that the level dummy is there, then we should identify whether, or let's say that both the dummies are not there, then we should identify that which is the one that we are trying to accept, right? So the null hypothesis clearly says that uh, so it tries to show the one-time jump in the level of a unit root process, right? Now let us look into the alternate hypothesis. So this is a one-time jump. Now if the one-time jump comes from a non-stationary process, an already non-stationary process, then it is not a structural change, right? One-time jump of an already non-stationary process. An already unit root process. Root process. Now, so this implies that if a jump, if a one-time jump comes from an already unit root process, then that's not a structural. Then the structural break is not significant. So basically, the implication is that if one-time jump if a one-time jump comes from an already unit root process, from an already unit root, then the structural break is not significant. The structural break is not significant. So this is what the null hypothesis implies. Now, corresponding to this, you have the alternate hypothesis. So the alternate hypothesis over here is A0 plus say A to T. So this is a trend stationary process plus mu to dl plus et. So the specification of et is that it follows a normal distribution with a mean 0 and sigma square. So what we have is h naught and h1. Right. So now this says that the one time now if this is a trend stationary process. So let's say over here in this case you can see that the trend is more or less it's a trend stationary process. You don't have any trend over here. You don't have a trend over here though. So if there is a one-time jump in this stationary process, then it will be approximated by that linear line. In such a case, then the alternate hypothesis will be so because before the break has happened and after the break has happened, the time series remains stationary, right? And it is that one-time jump which is causing it the non-stationary, which is causing the non-stationary. So we need to regress that, and what we need to see that out of this, which is the one which is getting the significant coefficient. Now, whichever of them gets a significant coefficient is the one that will be accepted, right? So this is the basic hypothesis or the basic hypothesis framework for the Chow test, right? So let's take a pause here for the day. There has been a lot of discussion that we have done today. So just go, I'll share over this Excel sheet with you. So just go through that, right? Go through this video recordings and just get your thoughts in place. And then we'll start off with the Chow testing process in details in the next session, from the next class onwards. In the meantime, I'll prepare your drive for the market risk sessions. Thank you.